questions pertaining to the homework? That helps with the graphing of it? Okay. Yeah, there are some drawbacks to the parametric plot, only that you have to adjust your range of t-values. Like there's like a window option where you adjust your window, and then I think by default, I believe it always lets t go between 0 and 2 pi. So you have to adjust it. But again, if you want help with parametric plot, just come by and talk with me. I'm happy. Or Google it, TI89 parametric plot help, and see what you find. I'm sure there's videos out there. Okay, so we're good then, homework-wise? Last class, we finished up with, this was the last thing that we did. Wait, was this the last thing we did? Yes, that was it. So what we had done is we had done this problem, the first time we did it using the standard way, which is to look at our slices as going up and down, like our rectangle went up and down. And then here I showed you that we could look sideways and make our rectangle be horizontal instead of vertical. And that when we do that, we have to switch our equations and solve them for x instead of y. And then we rewrite the integral in terms of y instead of x. And I just gave you one example of that. I want to do a few more of those today. And then we're going to move on to the next section. So let's take a look at something like find the area enclosed by x equals y to the fourth and y equals square root 2 minus x, and then y equals 0. So they actually give us 3 different curves here. There's 3 different curves, right? This one, and this one. So we need to find the region that's enclosed by those 3 curves. So let's try and draw this. Now, we might have a little bit of an issue with this one because it's solved for x. So you could use the parametric plot, or you can just try using like a t-table and get some points. You know it kind of looks like a parabola, right? Because it's a 4th degree polynomial in y, so it should open up to the side like this. This one right here should look like a square root function, right? So you could work that out. And then this one, y equals 0, is the x-axis, right? So let me bring in my graph paper here. That's what we used last time. See what I can do. Okay, y equals 0. I'll do that one first. So here's y equals 0. Whoa. Y equals the square root of 2 minus x. How can I graph this? How about just trying some points? Do we all know what a square root function looks like? I mean, just a regular square root function should look like this, right? Like a parabola laying on its side, cut in half. All right, so let's plug in some values. I can't plug in, well, I can plug in 0, can't I? Yeah, I can plug in 0. 0 would be the square root of 2. So I have 1.414, so it's somewhere around there. That's like square root of 2 right there. If I plug in 1, what do I get? I get 1. If I plug in 2, what do I get? 0. Oops, my first point needs to be redone. I don't know why I put it there. 1.414 is up here, then 1, then 0. And can I plug in 3? No, because it goes out of the domain of this, right? So you can kind of see what's happening here. This square root function doesn't go this way, it actually goes to the left. And that's because there's a negative in front of the x. So there's like a reflection. And you can plug in more points, but that gives us kind of a general idea of what's happening there. You've got this square root function. Terrible drawing. And then you have x equals y to the fourth. So let's plug in some values for y. What if you plug in y as 0? What do you get? X is 0. What if you plug in y is equal to 1? If I plug y as 1, what's x? 1. So if I go up 1 on the y-axis, my x is also 1. So it does this. If I plug in y as 2, what's x? 16. That's way out here, right? 16. So there's my parabola looking thing like this. Goes like that. Now it does go the other direction also. Goes this way. But I don't need it because do you see the region enclosed? It's the region that's enclosed by all three. So this one right in here. So if I'm going to do that region, would it be better to do my rectangles being vertical or horizontal? Horizontal? Let's zoom in on this real quick. Whoa. If I do vertical rectangles, that means like this. If those are what my rectangles look like, right? Then I have a top function and a bottom function. What happens is my top function, right, changes midway through, doesn't it? Then it changes to a different top function. So I would have to account for that, and so I'd have to have two separate integrals. As opposed to going this way, where my rectangle is horizontal instead, if I do that, then remember we turn our heads, we look this way. The top one would be the blue one, right? And then the bottom one would always be the black one as I moved up and down with this. So do you agree doing it horizontal would be better? Now when we do the rectangle horizontal, that means our integral is going to be with respect to y. When we do it vertical, it's with respect to x. So if I'm going to do the integral with respect to y, that means I need to solve all my equations for what variable? Solve it for x, yeah. Get it in terms of y, get each equation in terms of y, but each one has to be solved for x, all right? So that's what I'm about to do now. Well, wrong way. So I'm going to take each equation now. Let's see, I'll try and keep them color-coded. This one was the blue one. I have to solve that and get it in terms of x. So how are you going to do that? How do I get the x out of the radical here? Square on both sides, so square both sides of the equation. That releases the radicand from the radical. And then now just move things around, right? Can move the x to the left, move the y squared to the right. So I get x is equal to negative y squared plus 2. Right? And then what about the bottom function here? This bottom piece right here. It's the black one, right? Which needs to be solved for x. It already is. So I'm happy about that. So when we look at that rectangle, and I zoom in on that rectangle here, sideways, and here's my y-axis. We talked about this last class. What's the distance from the y-axis all the way to that right edge of that rectangle? Well, that's where that blue one came in, right? That blue one comes in like this. So it should be this blue one. So that distance should be what? Negative y squared plus 2. And then what's the distance to the bottom edge? Well, that's that black one coming in like this, right? I'm exaggerating those, right? then that distance will be the black function, which is y to the fourth. X is y to the fourth. So the distance, this actual length would be this one right here, the blue one, take away this one, right? So this distance right here will be the negative y squared plus 2 take away y to the fourth. Everybody following the construction here? Now we still need to figure out what our limits on our integral are, right? And since it's with respect to y, we're not looking left and right here, we're looking up and down, right? So where does this yellow region start, and then where does it stop? 0 and then 1. Now, how do we know it's 1? Because my picture was decent, right? But if you didn't know it was 1, how would you do it? You would set this equal to this, right? I'm going to do that because we need to at least practice with it. To find the intersection, I need to set y to the fourth equal to the other curve, and then I'll just move everything to one side. And this is an equation of quadratic type or quadratic form. It looks kind of like a quadratic equation, right? It does factor. It'll be what, y squared two sets of parentheses. What do we got? Y squared plus is that right? Negative 1 plus 2. Okay. Do y'all agree? Crickets today. Y'all all right? All right. So which of these can be set equal to 0? I mean, which of them is going to have an actual solution? Only the first one, right? Because this one, there's no way that this can ever be 0. Y squared plus 2, never going to be 0. Positive number, right? 2 plus a number that at least is going to be positive, right? Maybe it'll be 0, but that can't be 0. The whole thing can't be 0. So I just want to know when y squared minus 1 is 0, which means y must be plus or minus 1, right? But only one of those makes sense in this picture, the positive 1. Okay, so that's how we would have known. If your graphs are real good, though, then you can do it that way. All right, any questions? I'm going to set up the integral. So my integral is going to go from 0 to 1. It'll be the negative y squared plus 2, take away the other one, y to the fourth, and then dy, right? We can clean that up a little bit. Negative y squared plus 2 minus y to the fourth dy equals ... So you do the rest, right? Questions on that? No? Okay, let's do another one. Did I assign number 13 for homework? Okay. How about 15? Any problems with 15? Who's okay? All right. Let me give you a one that's come up before. People have had some issues with. Find the area of region in Q1, which means what? Quadrant 1, okay. Bounded by y equals x to the fourth, y equals x to the sixth. Both of these, x to the fourth and x to the sixth, are power functions and they're even, right? So they look like parabolas. We know that to start, hopefully. We know that they both pass through the origin, right? We know that at 1, they're both equal to 1, right? Aren't they? At 1, they are both equal to 1. And so one of them goes up like this, right? And the other one does the same thing. So which one is on top and which one's on bottom? Which one is it, though? Which one is between 0 and 1? One of these always stays above the other one. So which one's above and which one's below? X to the 6 is above. Why? Because I got a higher power, so it's above. You have. So let's think about this. This is why I'm showing you the example. That's the common mistake. Look, let's take the number 1/2, right? If I plug 1/2 in here, you take 1/2 to the fourth power. What's that? 1/16, right? If I take 1/2 and plug it into the other one to the sixth power, what's that? 1/64. Which one's bigger? 1/16, right? Is bigger than 1/64. So actually, it turns out that the fourth power one is bigger than the sixth power one, but only between 0 and 1 does that happen. Once you get past 1, then the x to the sixth takes over. So if you graph these, what happens is one of these does, oops, wrong color. One of these does this, and then the other one is like this. So once you get past 1, the blue one's on top. The blue one being which one here? The sixth power, and the red one being the fourth power. That's just I mean, the rest of this, I'll just set up the integral real quick, but I just wanted to make sure everyone was clear on the idea that, look, if someone says, if you take a number and raise it to a power, compared to a number raised to a bigger power, everyone always seems to think that that means the one raised to the higher power is going to be bigger. That's not necessarily the case. Depends on the number. If the number is in between 0 and 1, it's the opposite of what you might think. Am I clear on the point I'm trying to make here? Okay. So our integral setup here, I think we can get everything. We're going to do a vertical rectangle, right? Our rectangle is going to be in here like this, like that. Here's the x-axis. Now, I'm trying to do all this, even though we've done this a couple of times. I'm drawing everything out here because of what we're about to do in the next section, all right? This is our x-axis. The height here was what? What's the top one? It's x to the fourth, isn't it? And then the bottom one is x to the sixth. That's what's happening to my rectangle. So the distance here is x to the fourth minus x to the sixth. Since our rectangle is vertical, we're going to move left and right. So I need a left endpoint and a right endpoint, which obviously are 0 and 1, right? So my integral becomes 0 to 1 of x to the fourth minus x to the sixth dx. And we're done. I think we're good. I think we're good. Although, you know what, there's one more. Let's do 18 here. This looks like an interesting one. How about finding the area bounded by y equals the square root of x, not square root, absolute value of x, y equals x squared minus 2. So to do this problem, you have to know what the absolute value of x looks like, right? Just with a v, like this. That's the absolute value of x. And then x squared minus 2 is a parabola, which opens upward, right? But it's been shifted down 2. So it's going to look something like, I don't know, 1, 2, parabola goes up, that. Sorry, that's supposed to look symmetric. Doesn't look very symmetric. Like, I learned something interesting. It's not interesting. It's stupid, actually. But I was watching something about Pac-Man. I don't know. I just thought of Pac-Man. It looks like Pac-Man going up, eating something there. That originally the name of the game was going to be Puck-Man. It's going to be P-U-C, man. And they decided not to because they were afraid, you know, these arcades and these places, you know, kids were going to go scrape off the puck, the P for puck, and scrape off the edge of the P, and, you know, anyway, probably would have happened. All right, so what are we going to need to figure out here? I think it's obvious which one's on top and bottom, right? So we need the intersections. I need to know where those hit each other, where those x values occur. Also, I didn't mention this, but what about the rectangles? Should I go vertical or horizontal? Vertical looks okay, but we do have a slight problem, don't we? The vertical, we still are going to have a different red function. You know, to the left of 0, it's a line with a certain slope, and then on the right side, it's a line with a different slope, isn't it? So we'll have to split it into 2. Can we do it sideways? Can we do our rectangle sideways? Let me draw this one right here. Can you do that? What would be the top curve and the bottom curve? It's the same curve. That's not going to work. All right? There's an obvious problem there, isn't there? And then once I mean, that's enough of a problem. But even in here, what are you going to do? You can't draw a rectangle all the way across. So you'd have to break it into 2, and that would be a mess also. So let's just go with the easier of the 2, which looks like the vertical broken into 2 different scenarios. Left of 0 and right of 0. Sound fair? Could you also just get the area to the right of 0 and double it? You could do that also, but you would have to be damn sure you're positive it is symmetric. Which it is in this case, but I mean, in general, you might get yourself in trouble if you just say, oh, it looks symmetric. Here we know it is. All right, so I'm gonna do that. I think I'll use the symmetry here. Okay, so using the symmetry, I need to know where this parabola here hits this right here. So can somebody tell me what the equation of just this line is right here, the one I've highlighted there in green? It's y equals x, right? So if this one right here is just y equals x, then the intersection that I'm talking about just to the right of 0 would be when x squared minus 2 equals x. So I'm setting this red one here equal to the blue one. And that's a quadratic, isn't it? You get x squared minus x minus 2 equals 0. Factor x minus 2, x plus 1 equals 0. So what are your two solutions here? 2 and -1. Now, which one of them am I going to use? The 2, right? Because the -1 thinks that this line continues and hits it somewhere down here. But that's not even what's happening. So the 2 is our right endpoint. We good? So let's find this this total area. It's the integral from 0 to 2 of the top function minus the bottom one. Top one being x, not absolute value of x, right? Just x, minus the bottom one. The bottom one was x squared minus 2. Make sure you put a parenthesis there. Dx. That would be the area of just the right side, correct? So I will double that answer. So just put a constant in front, 2, and that doubles the answer. You could work that out the rest of the way. Any questions? All right. That's it. We're done with 7-1. I mean, yeah, 7-1. Let's get into 7-2 now. I think for your homework on that, just finish off. I would go back and revisit everything. I would probably look at, 5 through 20, just all of those. You've already done most of the odds there. Finish off the odds and go back and look at the evens. So page 369, 5 through 20, all would be a good set of homework for that section. All right, so now 7.2, volumes. Now, the concept of a volume is three-dimensional, isn't it? In order to have area, we just needed a flat surface, or a surface, and that's what we have in two-dimensional space. Now we're going to look at how we can use these things to do volumes. And we've talked about it, rotating these things around the axis and stuff. But let me just act like we haven't and set it up real quick. If we have two functions, f, and then we have a function on the bottom of this, that I'll make them connect at the end. They don't necessarily have to connect to each other. And then we look between the two endpoints A and B. If we want to take this region, which means take everything on the inside here, we already know we can find that area, right? But take that region and imagine wrapping it around the x-axis. So taking everything off the page, just bringing this whole thing out into three-dimensional space, and imagining that we can just, like a hinge, just swing the entire function around the x-axis and come back all the way up. If we do that, we get a solid, right? The question was, what's the volume of that solid? So the way we approached it is we take a vertical rectangle again, like this. Over here on the right-hand side, I'm going to draw the x-axis. Also notice right here on this axis right here, I'm going to draw a little arrow like curved. See that? You can even come and draw like this. That represents that I'm doing a rotation about the x-axis. I'm going to rotate this way. So the whole thing is going to go like that. If I do that, then what we call the axis of rotation here is the x-axis, right? Or you could say y equals 0. Y equals 0 is the x-axis, so our axis of rotation is y equals 0. Rotating about the x-axis, I have that rectangle that I'm going to wrap around the x-axis. So what is the height or the distance from here to here? That's what f is, right? Whatever f is. And the distance from here to here is G. Now, if I wrap that one thing around, right, that little rectangle, if I wrap it around in three-dimensional space, it would look like this. Wouldn't it? And my axis of rotation would be there. There's my x-axis. Do you all see the rectangle? It was right in here. And when I wrapped it around the x-axis, it created a washer, didn't it? Like a washer. So we have this washer and we want to know what its volume is. So what's the volume of that washer? Okay, so a quick reminder, if you have a cylinder, what's the volume of a cylinder? It's pi r squared times the height. Right? The radius, you need the radius of the cylinder. Pi r squared, isn't that just the area of that circle on top? And then the height is like its depth. So you're multiplying the area times its depth, basically. That would be the volume of a solid cylinder. What this is over here is like we have a solid cylinder, but we're taking out the middle of it. Right? That's what this washer is. Now our washer is has a very, very short height to it, doesn't it? And it's sideways, so it looks weird. But that is really a cylinder turned on its side with the cylinder cut out of the middle. Yes? So all we would need to really know is what's the volume of the whole cylinder, the whole thing, take away the volume of the inside cylinder, and that would be the result, wouldn't it? Does that make sense? So what would be, if I took this picture over here, what would be the volume of the solid outside piece? So what's the radius? What's the distance from our axis of rotation all the way out to this edge? What's that? That's F, right? That's F. Okay, I'm splitting this picture into two pictures. It's the solid piece, and then what would the inner one be? This one would be, I need to draw it a little bigger. So here's our axis of rotation. And then that height in here would be G. So what's the volume of this one on the left, according to this formula, pi r squared height? This volume would be pi times the radius. What's our radius? F. So F squared times the height. For us, the height, you have to, turn your head sideways. We're talking about this right here. And that was the infinitesimal width of the rectangle, which we always refer to as dx, right? So that's dx. Then we take away from that, right? We take away from that this one. So what's the volume of this one over here? Pi r squared, so pi g squared times its height, which is the same as the other one, right? dx. So the volume, and when I'm saying volume here, does everyone understand I'm talking about the volume of that piece right there? The volume will be, let's factor out some things that we have in common here. Like, well, we have a pi, right? We can take a pi out. We could also take a dx out, but I'm going to take the dx out the right side. You'll see. So I'm going to go f squared minus g squared and then dx. That's the same thing. That is the volume of that one washer. If I want the volume of the entire thing, I'm going to add them all up, infinitely many of them, right? And to do that, we use the what? The integral, right? So the total volume of the entire thing wrapped around the x-axis between A and B will be, and this is our final result here, the integral from A to B of this formula right here, right? But you can pull the pi out because it is a constant. So pi, and then it'll always be your f function squared minus the g function squared dx. That's our volume total. Total volume right there. I just don't want it to be mixed up with the volume of that little piece there. Does that geometric construction make sense? Yeah? I want to look real quick. I have this wind plot. I'm going to go to two-dimensional. I don't remember if this is going to work. I haven't done this in so long. Let me see. Let me try x squared. Let me just go from 0 to 2. Lock the interval. 3. Okay, so there I've got a little piece of a parabola. Like I said, I don't remember if I've done that, if this is going to. Okay, rotate. No. Volume of revolution. Here we go. About the y-axis. Hold on, I need to add something else. 0. No, that actually just computed the volume. I don't want that. Revolve surface. There we go. So I want to revolve that around the x-axis. Oh, come on. That might help. You see that? That's the parabola. When I rotate it around, it creates this. Now, it's supposed to be solid inside, all right? This right now is just getting the outside surface, which later on, would it be reasonable to ask what the surface area of that is? We will be able to do that, but it turns out it's harder to find the surface area than it is to find the volume. So wait, it'll come. Do you see it though, at least? Okay. All right, so let's try and do one of these. And again, it's mostly just going to be the setup. Okay, that's all it's going to be. Let's find the volume of the solid formed by rotating the region bounded by y equals x squared and y equals the square root of x about the x-axis. That's how most of the problems will be stated, something like that. Find the volume of the solid that's created when you take the region bounded by these two curves and rotate it around the x-axis. So what I'd like to see, because remember I told you I'm not going to have you on your test evaluating all these integrals. It's just set up, set up, set up. But you have to give me good pictures that demonstrate that you understand how you're setting the integral up. So here we go. I'm going to start by drawing a two-dimensional picture of the region. I'm going to need to know that the square root of x looks like this. I'm going to need to know that y equals x squared looks like this. Which gives me the region, which is right in here. I don't want the area, right? I want to imagine taking that, rotating that about the x-axis. So I need to somehow let you know I'm going to rotate about the x-axis, so I'm going to draw my little arrows here to show you I'm rotating about the x-axis. Yes?
I might be ahead of you real fast, but once you rotate it,
Mm-hmm.
aren't the functions going to be like the one we would originally use for our f would not be, it would be the lower one when we rotate it, like when we actually.
That's a great question. Because of the geometry, no, you wouldn't. Because of the geometry of this, we are doing. We're not technically rotating it. What we're doing is we're saying, what is the volume of this washer? To do that, all I need is its radius. The radius is the length of f. The fact that when I do like rotate it, it becomes negative later doesn't matter.
But even though it's on the bottom, like do we always choose it from the positive one? We take the
Top one, yes, and the
okay.
bottom, yes.
Okay.
Now we will have a little bit of an issue in a little while, but here's a way to look at it that'll resolve that right now. The top one, if you were, imagine you're standing on the axis of rotation, which was the x-axis, and you're looking out towards, you'll have your rectangle out there. The curve that's at the farthest away from you is your top function. The one that's closer to you is the bottom. Does that make sense at all? That's going to work for everything, yes. Mm-hmm. All right, so now let me draw my rectangle in here. I think it hopefully makes sense to draw this rectangle. And again, you might be thinking, okay, look, I already know that this integral is pi integral from 0 to 1 of what, x minus x to the fourth dx, and you're done. I understand like some of you can get that without even drawing it, but the drawing is part of what I want, especially because of what we're going to be doing in a minute, because we will not be rotating about the x-axis all the time. It might be instead a line down here, and then things get a little different. And if you trust your instinct, it might actually backfire on you. All right? So next to this picture, I'm going to draw my axis of rotation. Okay, there's my x-axis. That's y equals 0. I'm going to draw my rectangle up here. Sometimes I even like to come in here and draw the blue curve and just draw a piece of the red curve like that. Right, that's like that blue piece and that red piece coming in so that I can see really clearly what the top and bottom one are. So again, if I'm standing on the axis of rotation, all right, see, so imagine I'm a person standing on the axis of rotation. This is the flat ground, I'm standing here. And I'm looking out towards the thing that's going to be rotated. The function furthest away from me is going to be the top function. The one that's closest is this one. So my question is, from the axis of rotation, what's the distance from here to the blue? It's the exact value of that function, right? Square root of x. So this distance right here, from here to here, is the square root of x. What is the distance from here to here? X squared, right? And so by the formula, it should be pi integral from, we didn't talk about it, but you, I think, all are aware that that's 1, right? 1 is where they hit each other. So it's going to go from 0 to 1 of whatever that outer one, that distance was. What's that distance? Square root of x, but then squared minus the one that was inside, x squared, but then squared, and then dx. So pi integral 0 to 1, x minus x to the fourth dx, dot, dot, dot. Questions? That's it. Yep. I will say set up the integral that represents the volume of the solid found by rotating the region bounded by these two functions about the x-axis. And you will just set the integral up, and that's it. Yes? The volume, well, in this particular case, it would not be a cylinder. I mean, if I rotated that, it wouldn't be a cylinder. But are you saying this, the rectangle being rotated? Yeah, every time we rotate that rectangle, we're going to create a washer, right? There's another method, the next section, where we do something different, and it helps, but I don't want to get the carriage before the horse here. Okay, let's see if we can challenge you a little bit more with this. I want to do the exact same problem, but instead of rotating about the x-axis, I want to rotate it somewhere else, all right? Why? Is that what you said? Why? Yeah, well, we're not ready for that yet. We could, but let's wait. I want to do something else first. So right now, if I were to wrap this around, does everyone see kind of what it would look like? It's tough to visualize. It would be like this. If you looked at it from the side, you know, it'd be like a bowl. Yeah, but it's got, ah, man, I can't draw it. It's so hard to draw this. Let me try and draw it from, there we go, like this. But see, on the inside, it kind of like curves in, right? But it pinches off at this point, right? And you can put your hand in there, but then you'd have the walls on this, right? Y'all see that? That's that thing rotated around. And it has a certain volume. So let's do now the exact same problem. I don't want to copy all this down, so let's just go to a new page. Now, rotate about x equals -3. Y equals -3, sorry. Y equals -3. It's the exact same picture, but my axis of rotation is different now. So I go through the time, you know, I take the time to set up my picture. I don't like that. I liked my first picture on the other one. Sorry. There we go. I'm happier with that. So that's the same thing, right? We haven't changed anything here. But your axis of rotation is y is -3, which is down here. So I'm going to label my axis of rotation with the dotted line and show you where I'm rotating. Is that okay? I still want to rotate this region. I still want to use a vertical rectangle like this. But I think on this problem, you'll see the importance of setting up that next picture on the side. So what I had done before is I drew the axis of rotation over here, didn't I? This time it's y equals -3. My rectangle is up here, like this. And I'm even going to draw the x-axis in here. I'll put my blue curve in there, my red one in there to help us. It's almost the same picture, right? But I think with this we'll be able to really see this washer when it gets wrapped around, right? When it was around the x-axis, I wrapped it around, came around like this, and came back around here, right? It was something like that. So my washer was like no bigger than this, with the hole cut out of the center of it, right? This was my washer. Do y'all see that? But now, wrapping around this axis, my washer is like from here, like down here. The volume of that's going to be much different than the volume of what we had before, right? Because we have a larger gap in the middle. In fact, when I actually put it all together and I actually wrap this around, right? This whole thing. I could actually like jump through it, right? Because it doesn't pinch off at the origin anymore. Do y'all see the difference? So you're definitely going to have a different volume. How do we account for it? Well, same thing. Imagine you're standing on the axis of rotation, and you're saying, how far is it from here to that outer edge? What's the distance? It's this distance from here to here, right? From here to here is what? Square root of x. And then what's distance from here to here? 3. So the total distance all the way from here all the way to the axis of rotation is the square root of x plus 3. Do you see that I don't care that it's negative 3 down here? It's a distance, right? It's a distance. And remember, the radius gets squared anyway, right? So there's like almost, if you want to look at that cylinder picture we had before, right? This was our picture before. What we've done is we've found what I like to call the outer radius. We have found the radius of the outer piece, right? That's our outer radius. And then I need to find the inner radius, which would be from here to here, which would be what? X squared plus 3. Are there any questions on where I got that at all? Your integral is still going to go from 0 to 1, right? Still going to have the pi out front. But this time it's going to be that outer one, that long radius, the blue one, squared minus the red one squared, and then you evaluate. So it'll look like this. Our volume will be pi integral 0 to 1. This time it's the x square root of x plus 3 squared minus the x squared plus 3, but then squared dx. And that's all I would want on the test. I wouldn't need you to actually multiply that all out. But, I mean, could we evaluate this integral? Yeah, because this would, square that, you're going to have to FOIL it out. It would be all, powers of x. And this would all be powers of x, and then you could integrate term by term, bunch of power rule stuff. But no like, tough techniques of integration here, right? All right. Same problem, different place to rotate. How about that same problem, this time about y equals 4? Come through. I'm going to be kind of quick on my picture now. Red was on bottom. Y equals 4 is above this, isn't it? How are we with that? I know I'm going kind of quick here, but everyone see the axis of rotation, where it is, y equals 4. This time it's above it, isn't it? This is where I was telling you things can get a little tricky, all right? What's that? Yeah, now our axis of rotation is above our region instead of below it. So let's see. This is the way that I suggest you do this, all right? Again, what I'm giving you is just the way that I think made the most sense for me, so that's what I'm sharing with you. There's different ways to approach this, all right? So here's our axis of rotation. I'm going to also bring in the x-axis, which is down here. I'm going to bring in my rectangle, which is about right here. I have my blue curve there. I've got my red curve here. Right? All right. Now, you are standing where? Where do you stand? Your axis of rotation. You are looking out towards the rectangle, which means I'm looking down, right? Which one is furthest away from me? The red one's the furthest one this time, right? The outer radius of this washer is the red one. But it's the distance from here to the red. It's not the red one, it's this distance. So let's talk about that distance. We know only this, that from here to here is what? X squared. We know that's the distance, right? We're trying to find the distance from the axis of rotation down to that red one, right? Which is what? What is it? 4 minus x squared. Because we know the distance all the way from the axis of rotation all the way to the x-axis is 4. Because that's what it is, right? 4? It's 4. So if I take that whole distance and I subtract x squared, I get that distance. So you have this is 4 minus x squared. Now, same thing, trying to find the distance from the axis of rotation to the inner part, the inner radius now. 4 again minus that blue height, so 4 minus the square root of x. I'll do it in blue. Are there any questions on that? So the volume will be pi times the integral from 0 to 1 of the outer radius squared, 4 minus x squared, squared, minus the inner one, which was this one, squared. The volume is pi 0 to 1. Okay, outer radius, which was that, minus the inner one, which was this, dx. And then you could work that out. Now, I've been using two words here that I want, well, two groups of words that I'm going to rewrite our formula now for the volume like this, using, instead of doing the formula being pi integral a to b of f squared minus g squared, I'm going to do something else because I think it'll help you generalize. The new version, the reason I don't give you this in the beginning is because it would be difficult to understand what I'm talking about. I think it's going to be, the volume will be pi integral a to b of the outer, I'll say, how about this? R for radius out squared minus the radius of the in squared dx. Does that make sense to you, or does that just confuse you more? It's okay? Because when I say radius of the outer edge versus the radius of the inner edge, that accounts also for what your axis of rotation is. If you stick with the F and G formula, it's dangerous because if you go to an axis of rotation that's not the x-axis, it's not F. It could be like, what, 2 plus F, or it could be like we just did, 4 minus F. It could be these different variations. So this right here is not locking you down into wanting to just plug F and G in. It forces you to look at what that radius actually is. Questions? Yeah, so a picture that would go with this would be, you know, you have this, wherever your axis of rotation is, your outer would be this, and your inner would be this. What flipped? Like, I don't know if this is what you meant by flipped, but that would be your out, and this would be your in. You're always standing on your axis of rotation. Outer is the distance from the rotation to the outside edge of the rectangle. from the rotation to the inside edge of the rectangle. What if your axis of rotation goes through your rectangle? We don't do those problems, okay? We don't mess with them. Because it really doesn't make sense. As you start to rotate, it starts to go through its own volume, and it duplicates itself in certain places. So our axis of rotation will always be outside of our region. All right. Any questions or comments or concerns? Let's try something else. Find the volume of this solid of revolution. Now, solid of revolution is a term that's used to describe what we're doing right here. We're making solids by revolving things, right? We're revolving things around certain axes. They're called solids of revolution. So we'd like to find the volume of this solid of revolution. Let me give you the region, okay? Here's the region. Your region that you're going to rotate is going to be the one bounded by these curves. X equals y squared minus 4. X equals 4. And I want to rotate this about x equals 6. Okay, so I just turned up the difficulty a little bit on the problem, all right? Let's see how this becomes a little bit weird. Not weird, it's just going to be, we're going to have to think through this a little bit. First thing we need is the region, right? I mean, you're not going anywhere without the region. So what does this look like? What does x equals y squared minus 4 look like? Parabola sideways though, right? What does x equals 4 look like? Vertical line? And we're rotating it. Whenever you see about, that means that's your axis of rotation. So we're taking this region about x equals 6. That's another vertical line, isn't it? Vertical line. So here I go with my drawing. I'll do x equals 4 first. That's one of my curves. X equals 6. This is my axis of rotation. So does everyone see that now instead of rotating this way, right, I'm actually going this way. I'm going to rotate it around like this. Because my axis of rotation is now vertical instead of horizontal. Now I need the x equals y squared minus 4. We said that's a parabola that opens up sideways. Where is it? Down here somewhere. Here's negative 4. And it goes like this. Oh, geez. That's all right. That'll work. That's my region. I want to rotate that about the x-axis, or not about the x-axis, about x equals 6. Y'all see it? Almost going to look like a donut. I mean, not really, but right, kind of like flying saucer with a hole punched out of the center of it. Y'all see it? What's different here? Your rectangle cannot be vertical, can it? Because your top and bottom would be the same parabola, and that's just not going to happen, right? So your rectangle has to be horizontal. So my rectangle is going to come in here. It's going to be like this. Y'all agree? When I rotate that around, I'm still going to get a washer, right? Still going to get some sort of washer. And I can still do the same exact logic that I just did. I can stand on my axis of rotation, and I can talk about an outer radius and an inner radius, can't I? Right? Outer and inner. So let me draw a picture. I think I'll do this one below it. I have my y-axis. I have my axis of rotation. I have my rectangle in here. I have the blue curve that's cutting here, and I have the red curve, which is a straight line that's there. Y'all see that picture, that rectangle here? What is the outer radius? This is the tricky part. What? Okay, y squared minus 4 is the blue function, right? Y squared minus 4. Y squared minus 4 gives you this distance from the y-axis to there. That's what it gives you, right? That right there is y squared minus 4. Because y squared minus 4 gives you your x coordinate, doesn't it? So it gives you this x value, which is really the distance from 0. So just this little piece from here to here is y squared minus 4. Did y'all buy that? And then you have this distance, which is always going to be what? 6? It's from here to here? Okay, do y'all agree with this or not? Pardon me? Okay, so we put them together, right? Would give you that. But do you agree with this construction so far? Let's take a specific particular point right here. Let's say that tip right there. That rectangle would come all the way down, right? Like this. What would that distance be from here all the way to here? Sorry, to here. What would that be? That'd be your 6 plus is 4, which would be 10, right? Agreed? 10. So that outer radius would be 10. All right. So that's what would happen. That point, that red point comes when y is what? What's your y value that would get you out to here? When y is 0, right? So when I plug in y equals 0, I should get this distance to be 10. Does it work? What's negative 4 plus 6? It's 2. Something wrong with this formula. You have to realize here that this distance right here, because it's to the left of the y-axis, is actually a negative value. You need it to be positive, right? You need it to be added on to your distance. So there's two ways of resolving this, all right? There's two ways. We can realize that and change this by a sign, which would make it, instead of y squared minus 4, it would make it 4 minus y squared, right? We could do that. Or another option would be, and this one I think is more difficult, is to imagine the same picture on the other side like this. Something like that, and trying to rotate around this one. I think this is more challenging, but it makes, you have to come up with a new equation for this new parabola, and I don't think it's worth it. So we have to realize here that this distance must be positive, right? I'm going to put a little plus sign there, which means I'm going to make it 4 minus y squared. Now, put that together with this, and what do you get? The 6 is going to be 6, right? So add those together, and what do you get? 10 minus y squared? Now check it. If y is 0, how long is the rectangle? 10. Or the distance to the outer would be 10. That's a subtlety that you have to be extremely careful with. And then, what about the inside, this red one right here? The distance from here to here? 2. Always 2, isn't it? Because that's always 4. That's always 6. The entire time you move that rectangle down, those rectangles down, you get that. So that's just 2. So what would be the outer radius would be this, right? And then squared, and then minus the inner radius, which is 2 squared. Integral goes from, it's pi integral from where to where? We haven't resolved that yet, have we? So let me at least set up the integral. I won't get the limits of integration on here yet. It's the outer one minus the inner one dy, not dx, right? Because we've turned sideways, our rectangle, our reference rectangle there is going to be horizontal. So we're going to integrate with respect to y. What about those limits of integration? How are you going to get those? Yeah, you need to know when this parabola, right, hits this. So you need to get that intersection. I can do that work right here. Intersection. For the intersection, I'm going to set negative y squared. No, it wasn't negative y squared. It was y squared minus 4 equal to what? 4. So y squared equals 8. So y is equal to plus or minus the square root of 8. Right? Those are your 2 points, plus and minus 8. So that's your negative root 8 and positive root 8 here. And we're done. You see where that problem was tricky, right? It could happen on the x-axis also. Yeah. But the example I gave you on the x-axis, I kept everything in that first quadrant on purpose. Yeah. This is a good example of how you have to take into account where it lies and truly be looking at the distance. And when you're in doubt, just give yourself a couple of examples. Like I gave myself that example, like what would happen if y was 0? I mean, yeah, if y was 0, I'd need that to be 10. Does my formula make that happen? No, something's off. There's a little thought that has to be put into these. Okay. We're going to go into a slightly different type of problem now. We're still in the same section. A solid has as its base the region bounded by y equals x, and y equals x to the 4th. All right, this is not the end of the problem, okay? Let's just at least get our heads around this part. There's a solid sitting out here, okay? Here it is, whatever, here. Boom, I just put it on the table, okay? Its base, okay, so when I put it on the table, it leaves an impression on the table, right? What it's covering on the table is equivalent to the region bounded by those two curves. All right? That's what it looks like where it touches the ground. With me? What it looks like above, I haven't talked to you about. Now I'm about to tell you what it looks like above that. Perpendicular, I'm just going to say perp, cross sections, which are parallel to the y-axis, form I have many options here. Squares. We'll start out with squares. Find the volume of this solid. I'm going to point out now that this problem is different than a solid of revolution problem, okay? I'm not giving you an axis of rotation. I'm actually giving you a solid, and I'm describing how it's formed, what it looks like, and you're supposed to give me the volume of it, all right? Very different procedure. So in this section, there are kind of two distinct types of problems. There's the rotation problems, and then these. All right, so we need to get an idea of what the hell this thing looks like and what this all means. Okay, so what does the perpendicular cross-section mean? Well, let's orient ourselves in this room so y'all can see me here. We have, let's say, this corner of this desk. This is the x-axis, okay? This is the y-axis, and this is my sheet of paper on the ground, right? I put this solid down on the table, x-axis, y-axis. I know what the shadow on the ground looks like, right? The shadow on the ground looks like the intersection of those two, or the region enclosed by those two curves. Okay, that's what it looks like down here. Which to me, it's a line, right? Y equals x. And then it's like a parabola that comes up, right? Something like that. Now, it says that when I take perpendicular cross sections, which are parallel to the y-axis, what that means is I come in here with a knife, okay? And I get my knife parallel to the y-axis, but perpendicular to the actual ground. So I want to make sure I hold my knife parallel to the x-axis, to the y-axis, right, y-axis, and keep this knife so that when I slice, it's going to go straight down, not at an angle, okay? Perpendicular cross-section parallel to the y-axis. Got it? When I come through here and slice through this, and look at it from the side, what it forms are squares. So when I pick that cross section up and look at it, it's a square. And every time I slice, I get a square. You'll kind of see it a little bit. Now I'm going to try and draw it, because it's kind of tough to draw, but we'll do our best. Okay, first thing I'm going to do is draw the actual region in two-dimensional space. X, Y. I have a line. That's y equals x. Then I have the x squared, or x to the fourth thing. It looks like this. And so my region here is this. With me? That's what, when I set it down on the ground, that's the part touching on the ground. Now, if you come through and slice it, right, just one slice, come through and slice, then where I cut it right there, and I pick it up, it's going to be a square. Now, square means what? All sides same length, right? So if I were to slice it right here and look at it from the side, that square each side would have this length, wouldn't it? But if I sliced it here, each square would have length, the length of each side would be this small, right? And if I got even closer, right, then the square is going to be small. Yes? And if I do it like kind of, right about here, that's going to be like the biggest square I get, right? But as I keep moving to the right, what happens to those squares? They get smaller and smaller and smaller. Y'all with me? So I need to get my head around what the hell that's going to look like. So I'm going to try a three-dimensional picture. And try it. Here's one way you can draw three-dimensional. Here's X, here's Y. I know that on the ground, it looks something like this. Again, this is going to take some time and practice. There's my parabola-looking thing on the ground. Here's my other piece, right? That's like, here's my X and Y. It's like we're standing where you are, looking at it. We see our X-axis, we see our Y-axis, we see the thing on the ground. And I really think that I need to exaggerate the heck out of that blue one. So let me bring it in like this. Really exaggerate it. Whoa. Now, when I come through here and slice, it'll be like this, right? There's my slice. Oh, I don't like that slice. It's got to be parallel to the y-axis, doesn't it? There's my slice on the ground. And then I'm going to make a square out of that. So I'm going to go up the same distance, over the same distance, down the same distance. If I come to here, go up the same distance, over same distance, down. It's a bigger square. Come in over here, up that distance, down. Right in here, like that. Do y'all kind of see that? It's hard to do this. It's hard to draw it. And the drawing is not that important, all right? But I'm trying to get you to see what it looks like, kind of. If I connect these edges, it looks something like that. And it'll pinch down over there. And it comes up like this. And it pinches down like that. You kind of get an idea of what it looks like this way. But the big thing for you is to come up with the formula that gives you that volume. So imagine what we're going to do is we're going to take a slice, right? Slice through, take that little cheese slice, right? And find its volume. What's the volume of one of those slices? And then we're going to add them all up. And that means we'll use an integral, right? So take one slice here. Take that slice right there. Tell me about that slice. It's going to have, it's going to be a square, right? It's going to have a little bit of thickness to it. What's that thickness going to be? How wide is that slice going to be? If I'm going to do an infinite number of them, it's dx, right? So that's going to have a little infinitesimal width to it of dx. I'll try and label it here, dx. It's a square, so all these sides are the same, but what is the length of one of the sides? What is it? Yeah, what's this length right here? What's that distance? It's the upper function, right, which in this case is x. Take away the bottom one, x to the fourth. So this distance right here is x minus x to the fourth. And since it's a square, this side is also x minus x to the fourth. And all the sides are x times x, x minus x to the fourth. So what is the volume of that little piece right here? This times dx, right? That's the volume of one infinitesimal slice. Now you want to add them up, right? You want all the slices starting at x equals 0 all the way to, where do they hit each other? Where do those two graphs hit each other? 1? So the volume of this solid will be integral from 0 to 1 of, what did you say? X minus x to the fourth times itself again, right? So squared, then dx. That's it. Questions? I'm going to give you one more of these, but we're going to use the same exact problem. But remember when I said that the perpendicular cross sections parallel to the y-axis made little squares? What if instead they made little, like when you cut it and you opened it up and you looked at it from the side, it made a little semicircle, a half circle, instead of squares? So same exact problem, but I'm going to say the perpendicular cross sections are half circles. That one piece right there looks like this. On the ground, it's a half circle like this, has a little bit of a width to it. Do y'all see that or not? We're taking that, imagine that's on the ground. We look at it from the side where we cut it. It's got an infinitesimal width to it. And, Okay, good. So instead of using the square, area of a square, right, we just need the area of a half circle, right? Half a circle. So what's the area of a full circle? Pi r squared, right? So we want half of that. So we know the area of this will be 1/2 pi r squared. But what's our radius? The radius would be from the center out, right? We don't know that right off the bat. What we know is the distance all the way across. What's the distance all the way across? You already told me that last problem, right? X minus x to the fourth is all the way across. So our radius is actually half of this, isn't it? So this would turn into, up here, would turn into 1/2 pi, I'm going to run out of room there. 1/2 pi times whatever our radius is squared. But what did we say our radius is? Half of this, right? So half of the x minus x to the fourth is our radius. That's this, half of this. That squared times pi, that's the area of that front side. Then times dx would give us our depth, and that would give us our volume of that one little slice. Question? Oh yeah, I'm sure we could. Square the bottom, you get you get the 4, pop it out here, it's 1/8. And I'll do that. I have integral, let's see, we're going 0 to 1. It's 1/8 pi, and then I'm just going to leave that as x minus x to the fourth squared dx. Are there questions on this right here? Why is it half of which one? This right here? Okay, the formula for the area of a circle, remember this is a half circle, right? No. The area of a full circle is pi r squared. We don't want the full circle, we want half of it. So the area of this half circle is 1/2 pi r squared. But I need to know the radius. The radius is half of the diameter, right? I know the diameter because the diameter is where I cut it. The diameter is all the way across this. That is x minus x to the fourth. Diameter, though. Half of that is radius. So I take that and divide by 2. If it says half circles. Another one would have been the same exact setup, but perpendicular cross sections form equilateral triangles. So now what you have is your picture here. Instead of being this, I'll just go to a new page. Your picture would look like this. You still have a width of dx. This is what? I'm going to put up here, equilateral triangles. This is x minus x to the fourth, but you need to find that area. So what is the area of a triangle? It's normally 1/2 base times height, right? But you don't have the height, do you? But there was another formula. Do I remember this one? 1/2 AB sine theta. Anyone remember that area formula for a circle? A triangle. If you have a triangle, if you know what the height is and you know what the base is, then 1/2 base times height. But if you don't know the height, which a lot of times we don't, and instead what you do know is this side, and the angle between them, then the formula becomes 1/2 AB sine theta. And for us, do we know the angle between all these sides? Well, it's an equilateral, right? So all angles must be the same, which means that's a 60 degrees in here, right? And if all sides are the same, then this side right here is also x minus x to the fourth. So the area of that would be 1/2. A times B would be this times itself, so squared, times sine of 60 degrees, which is root 3 over 2. So the volume of this particular example would be integral 0 to 1, and then what? Root 3 over 4x minus x to the fourth squared dx. That's about the most you ever see. Perpendicular cross sections are squares, equilateral triangles, half circles, and full circles. But the full circle wouldn't be much different than the half circle. We just wouldn't divide by 2. Okay, I think we've exhausted ourselves here. For homework here, page 378. One through 18, odds, then evens. And I would say just setting these up, just setting them up. And then all of those are problems of where solids of revolution. Numbers Numbers 39 through 42, or actually 43, are problems that you can look at that are just like the ones I did right now, where you did the cross sections. Those are good problems to mess with. And that's it for 7-2. It's really just going to be you go home and practice, because There's little things here and there you got to get used to doing and graphing and yes, sure. I'm gonna stop